11G release to grid infrastructure services. Here I would be talking about the startup sequence of how the daemons are started for a clustered environment in 11G release 2. Basically the OHASD architecture followed by what follows after OHASD. On the way through, after understanding the startup sequence, I would also explain you what are the different daemons for your grid infrastructure services in 11G release 2, what is the role. Some of the critical components such as grid plug and play daemon I would discuss in detail. I would also explain on the way through that how grid plug and play profiles are protected by valid. Then I will walk you over some of the diagnostic collection methods, the log and trace file locations, and then what is the cluster health monitor, which is an embedded tool that comes nowadays with 11G release to grid infrastructure services. What are the further readings for it? What is OLR? What is OCR? So we'll discuss each of these components in detail. It may roughly take an hour's discussion or so to understand these components. So let's first understand the startup sequence. Now I am revisiting this topic which we have already done, but since it was not recorded anywhere, I thought of putting this one slide discussion to understand the startup sequence for 11G release 2 grid infrastructure software, the clusterware. So on the node, which is already part of your cluster, I am assuming that you are using Unix like operating system or Linux. So once your operating system finishes the bootstrap process, it reads etc init tab file via the initialization daemon named init or initd. In the init tab file, I will also show you on the actual box, the last line of your etc init tab file is the one that triggers Oracle High Availability Service Daemon, the OHASD framework. Now understand in short what is OHASD. It comes in two flavors, OHASD for cluster and OHASD for non-RAC environments. When we talk about OHASD in case of cluster, we typically refer to it as CRS. When you talk about OHASD, which is nothing but an Oracle Restart product, in a non-RAC environment, we typically call it as HAS. So CRS terminology comes in a RAC environment. HAS terminology comes in a non-RAC environment. But ultimately what is that I am talking about? I am talking about a product named Oracle Restart, which is bundled as part of your grid infrastructure software suite, which is also called as Oracle Clusterware. So often during discussions, different people would refer to the same software using the analogous terminology. So you shouldn't be confused. So when I talk about Oracle Restart, I am referring to OHASD, which is the actual implementation daemon, the Oracle High Availability Service daemon. It can be installed in case of a RAC as well as in a non-RAC environment. In a non-RAC environment, you typically install Oracle Restart when you create a non-RAC ASM configuration. So where it is typically named as Oracle Restart. But when we refer to OHASD in a cluster environment, we say CRS. And when we refer to OHASD environment in a non-RAC ASM implementation, we refer to it as HAS, which is a High Availability Service. In either cases, whether it's RAC or non-RAC, the software is triggered via the initial entry point as init and through the configuration file etc init tab. So init triggers OHASD and OHASD init on its own triggers CSSD agent, Aura root agent for privileged activities, and for non-privileged activities it triggers Aura agent. CSSD agent internally triggers CSSD, which is the Oracle Cluster Synchronization Service Daemon, which is responsible for heartbeat and node membership. Whereas certain other privileged services are started as Aura root agent. I told you earlier the reason that certain daemons would run in your cluster infrastructure as root. All such privileged activities or the daemons that you would like to start as root, you don't have to do anything. They are automatically started by the background process Aura root agent. Those daemons themselves are CSSD monitor, CRSD and CTSSD. CSSD monitor is nothing but the Oracle Cluster Synchronization Service Daemon monitor. CRSD, which is responsible for starting cluster application resources, the cluster ready service daemon, and CTSSD, which is a cluster time synchronization service daemon. Until 11G, the time synchronization responsibility between clustered node was purely vested into some of the well-known operating system provided services such as NTP, Network Time Protocol. But nowadays Oracle has a built-in facility where the clusterware software itself can synchronize time on the clustered node so that there isn't any time skew between them. Prior to that it was all driven through NTP. A common question is CTSSD still there if I use NTP? Is CTSSD still there if I do not use NTP? Answer is yes. CTSSD is always there whether or not you use the underlying operating system mechanism NTP. The only change is in what mode CTSSD operates. It might operate in active mode if the underlying NTP mechanism is missing. It operates in an observer mode if underlying NTP method is enabled. So CTSSD is always there whether or not you use NTP. The only difference is whether it takes charge of time synchronization, active mode, or whether it simply acts as an observer of time skew, which is in case of you using NTP at a OS level. CRSD is responsible for starting cluster application resources, both privileged and not so privileged. So when it comes to starting privileged cluster application resources, which includes grid name service daemon GNSD, the scan single client access name virtual IPs for your node, whether it's attaching the virtual IP of your node to your node or to somebody else. In the case of your node going down, the VIP fails over to another one. So detaching it from your node, attaching it elsewhere. Whether it's configuration of GNS VIP, which is used in case of GNS based RAC implementations, where GNS is a subdomain delegation within your DNS. So you need to have a virtual IP for that entity as well, which is called as a GNS VIP. Or whether it is attaching the HA IP to your machine. All of them are privileged activities and are hence taken care by Aura root agent pop-up process, which emerges, spawns out of CRSD, or CRSD spawns that privileged process Aura root agent, which in turn takes care of starting the other daemons. There are other non-privileged resources part of your cluster which does not require operating system elevated privileges. All such resources are started as a regular Oracle or Aura Grid user, as may be the case while implementation, and are started by a spawned process called as Aura agent. They are your regular listeners, which listens on the public and the virtual IP of a given machine, scan listeners, which listen on the scan VIP, ONS, the Oracle Notification Server daemon, which is used for propagating the local events to all the ONS clustered nodes, database instances for whatever databases you have on that machine and their respective instances, the EONS daemon, which is again part of the notification service, and the Oracle ASM instance configured for your node. All of them are started as non-privileged activities which are done by Aura agent. And the Aura agent triggered by OHSD also takes care for multicast DNS daemon, MDNSD, EVMD, which stands for Event Management Daemon, the Oracle ASM, which is nothing but linked with your Oracle instance, the entire ASM, clustered ASM environment, and more importantly, the grid plug and play daemon. We will discuss in detail what is grid plug and play. So this is the startup chronology of how the cluster services are started for 11G release 2 clusterware or grid infrastructure services. Now in details, we will go over each of those daemons. I said there is one daemon which in turn triggers Aura root agent and Aura agent to start up privileged cluster resources and not so privileged clustered resources. That task is vested into cluster ready services, the CRSD daemon, which at a OS level you will see as CRSD.bin. So I am checking it on my OS. This is the one which often runs with the argument as reboot. So let's understand what does this means. So it runs as root. See here which is the PPID, parent process ID for it is 1, which means init. So it is called indirectly via an init. I know that the calling mechanism comes via OHSD, but the parent of this one is init. It runs from your grid home with a reboot argument. It is responsible for start, stop, monitor and failover of your cluster application resource. It is also responsible for maintaining Oracle cluster registry and also restarts the resource when the failure occurs. So if one of the resource abruptly goes down, including your database instance, it's the responsibility of CRSD to bring it up again without human intervention. So consider a case that on a given node I abruptly aborted ASM instance. What will happen to the associated database instances running on that machine? They would be also abruptly terminated because the bridge, ASM bridge between the database and the ASM is broken. Whenever this happens, my CRSD will detect this because it is continuously monitoring it. The moment it detects this as an abrupt failure, it will bring up the ASM instance. It will also automatically start the database without human intervention. So this is what I said. It maintains OCR and also restarts the resources when the failure occurs. In my case, the failure was an abrupt shutdown of an ASM instance. This is applicable for RAC systems. For Oracle restart and ASM, instead OHSD is used. So in case of a non-RAC environment where I implemented grid infrastructure for ASM configuration, instead this job is accomplished by OHSD in a standalone non-RAC environment. Next one is Cluster Synchronization Service, CSS or OCSSD. You can check it by saying ps-ef grep CSS, and as I said in my previous slide, there is a CSSD monitor there is a CSSD agent, and then there is a OCSSD.bin process. Let's understand what's the role of each one of them. CSSD monitor monitors for node hang and subsequently acts as a OPROC-D daemon which was there in your 10G clusterware. So in 10G there used to be a separate daemon called as OPROC-D, which acts as a fencing daemon. It acts as a IO fencing. Now IO fencing is a process of barring a node from doing any IO the moment heartbeats are missed. So if a given node misses a heartbeat, you certainly do not want that node to be part of your cluster. And that's where we said eviction happens. That eviction may be with a reboot or without a reboot, called as a rebootless eviction. The purpose behind this one is that my node, errant node I would call it as, which is no longer responding to the cluster communication protocol, the heartbeat mechanism, should no longer do an IO, and if it still does an IO, it could result into corrupted data blocks, because my cluster services are no longer doing the cache coherency. They are not communicating with each other. So there is no synergy between the work being done by node 1 and node 2, because they are no longer talking terms to each other. So such errant nodes must be barred from doing any IO. This process is called as IO fencing. The IO fencing part earlier in 10G release 2 was carried out by a background process called as OPROC-D, which now is being done by CSSD monitor. So monitor for node hang via OPROC-D functionality and monitors OC, there is a typo here, OCSSD process hangs via OCLS OMON functionality, and monitors vendor cluster where, if you are using a vendor cluster where, using VMON functionality, which is for vendor specific cluster monitor. This is a multi-threaded process that runs with a elevated priority. Now by elevated priority we mean, if you check the PRI column or the nice value column of this process, it is slightly at a higher priority level than any other process in your cluster. That's what is called as an elevated priority. The startup sequence for this process is init triggers OHSD, which is init.ohsd. OHSD triggers OHSD daemon, which is the script in your etc init.d, and in turn it calls OHSD.bin, which is in your grid infrastructure home bin directory, and OHSD bin triggers CSSD monitor. The CSSD agent is spawned by OHSD process. Previously 10G OPROC-D used to do this job, is responsible for, as I said, IO fencing. So the monitor monitors OPROC-D, but the actual functionality of OPROC-D is being done by CSSD agent now in 11G R2. Killing this process would cause node reboot. So it runs as a fatal process, mandatory background daemon. So the moment you kill a CSSD agent, there will be an eviction or a node reboot. It starts, stops, checks the status of OCSSD.bin process or the daemon. The startup sequence is init triggers init.ohsd, init.ohsd triggers OHSD, OHSD triggers OHSD.bin, and OHSD.bin triggers CSSD agent. OCSSD.bin is one of the third from the CSS category. It manages the cluster node membership. It runs as a regular user. It doesn't run as a privileged user. Failure to this particular process results into node restart. So do not kill this process. The moment you kill it, your clusters where will evict that particular node from the cluster. The startup sequence is init triggers init.ohsd, init.ohsd triggers OHSD, OHSD triggers OHSD.bin, OHSD.bin triggers CSSD agent, CSSD agent triggers OCSSD, and OCSSD actually triggers the actual executable program, which is in your grid home bin, OCSSD.bin. Next one is event management daemon, EVMD. You can quickly check it by saying ps-ef grep EVM, and you would see there is evmd.bin, evm logger.bin, and which actually starts logging all the cluster events in a log file, which is evm logger.log. The location is always in grid home evm log. evmd.bin distributes and communicates some cluster events to all the cluster members so that they are aware of any cluster reconfiguration or significant events that has occurred on a given node. So it's a propagation mechanism. Whereas evmlogger.bin, which is started in turn by evmd.bin, reads the configuration files and determines what events from the huge set of events that evmd generates to subscribe to from evmd, and it also runs user defined action for those events called as callouts. So this whole mechanism is called as FAN, fast application notification, and user specified action on top of it when a given event occurs, called as a callout. A callout is nothing but a user specified action. Well, this is only required if you want to trap a specific event and take some corrective action instead. Now we don't do this for regular resources like all the ones that comes out of box with your grid infrastructure. Basically the listener, the scan listener, their virtual IPs, databases, services, ASM instances. We don't do this trapping and corrective actions for any one of them. Then what is this mechanism provided for? This is typically done for additional applications that you have deployed on top of your clustering framework. You can also remember, this does not, Oracle Clusterware is not meant only to be used for Oracle products. You can use any of your custom software, register it with your Oracle Cluster registry as a custom application with a custom application VIP and make it HA, highly available. Consider a case that I had a Java application server or a web application server, let's say Apache. I have deployed it on top of a cluster. So I will register Apache as one of my custom application resource. Apache runs on some IP, some port number, typically port number 80 or any other port, 8080 for that matter. So it will listen on some particular IP. That IP I am assuming is an application VIP which keeps on floating between node 1 and node 2. So I have registered an application named Apache with its own application VIP which can float between machines like your node VIP. So when node 1 is up and running, my Apache runs on node 1. The moment my node goes down, I can trap this event. I can manually force that application VIP to migrate on another node, and once it migrates successfully, I can ask my Apache web server to start on another node. So you can make use of the Clusterware framework for registering your custom applications so that they can utilize the HA facility which is provided to you by Clusterware framework. So you can also register any custom applications that you want to make it as a floating application between, for HA purpose, between more than one nodes. The Oracle root agent process can be seen by saying ps-ef grep aura root agent, and you would see aura root agent.bin and probably more than one processes. Because I told you there are two aura root agents spawned. So aura root agent.bin is a specialized aura agent process that helps CRSD manage resources which are owned by root, such as network. So anything related to the network IPs, whether it's a VIP, scan IP or HA IP, or the GNS VIP in case of GNS implementations. So the above two processes are actually threads which looks like a process, and this is very Linux specific. So they are the because we have seen earlier that there are two aura root agents triggered, one by CRSD, one by OHASD. Then next one is cluster time synchronization service, CTSS, or CTSSD when it comes to daemon, you can check it by saying ps-e upgrade CTSS. It runs as root. Remember, if I want to run cluster time synchronization which will take care of adjusting the gap between two machine times, I can't do it as a general user. So the service itself runs as a root. Well, how internally it runs it? It depends. So ctssd.bin provides time management in a cluster for Oracle clusterware. CTSSD is only designed to work with mainstream time synchronization softwares like NTP. So if you use any other mechanism other than NTP for time synchronization, don't expect CTSSD to detect it. So it is only hard coded to work with NTP to an extent that if the file etc.ntp.conf or xntp.conf in case of Linuxes, it will check the existence of that file and accordingly it will take a decision. Shall it start in an active mode or in an observer mode? So if the files are present, whether or not you have configured NTP, it will assume that you are running NTP at OS level, and then CTSSD will itself start as in observer mode. But if those files are missing, then it will safely assume that there is no NTP configuration at OS level, and then it will start in an active mode. It checks if CTSSD is running in active mode or in observer mode. You can do so by saying CLU VFY COM clock sync. So I am going to grid home bin and then I am saying CLU VFY component clock sync. So it will show you whether it is running in an active mode or in an observer mode. And to this effect, because the very working of this process is not clearly documented in the official documents, you may have to visit Metalink. So see here, in my case, it is running it in an observer mode. Now, why it is running it in an observer mode? The reason is that at a OS level, we already have configured NTP with a clock sliving option -X, and now I am relying on the OS mechanism of synchronizing the machine time. So CTSSD is still there, but in this case it has started itself as an observer. So it is not the primary process to take care of time synchronization between clustered nodes. That's being done by your NTP. There are quite a few behavioral problems with CTSSD, I told you, because it's not very clear cut documented. At times you may have to go on to Metalink to find out why it is not working. I will tell you an example. Somebody never configured NTP. So how should CTSSD start now? In active mode. But people have discovered that although there is no NTP, CTSSD is still running in observer mode. There was another case reported by another one. He said, I have configured NTP, but my CTSSD is still running in active mode. So there are some quite abnormal behaviors with respect to that. But if you follow the correct documentation, you will see a result similar to what we have seen. So in our case, NTP is configured. So CTSSD is running in an observer mode, which is the correct configuration. It may select any of the two modes, active or observer, depending upon the existence of the file etc ntp.conf or etc xntp.conf. So depending on that, it will automatically pick up what mode to run the clock synchronization service into. Then there is a ORA agent, whereas the previous one was ORA root agent. ORA agent again is spawned by multiple processes. One is triggered by OHSD and another one is triggered via CRSD. ORA agent.bin extends clusterware to support Oracle specific requirement and complex resources. This process runs server callout scripts when FAN events occur, fast application notification, and the user specified callout script, the action script, they are actually run by the Aura agent process. This process was in the earlier version known as RAC. Nowadays it's renamed as Aura agent. Now when you look at the OHASD service stack, you would see there are a couple of processes rather which are coming from the OHASD. Now it's independent of whether it's cluster or whether it's a standalone installation. But some of them which are very cluster specific, which are part of the Oracle High Availability Services grid infrastructure for cluster, is cluster logger service. The cluster logger service can be seen as OLoggerD. So which is receives information from all the nodes in the cluster and persisting or is part of the CHM, which is a cluster health monitor tool that comes nowadays with 11.2020. So if your Oracle version is 11.2020 or higher, CHM tool is by default built into your clusterware, the grid infrastructure software. So this OLogger process captures the cluster health monitoring logs in one centralized location. That centralized location is called as a repository. That repository is made up of Berkeley DB. That Berkeley DB is now it's a separate database. It's a file-based repository called as BDB. So whatever diagnostic information it collects, the CHM tool, it is logged into the Berkeley DB by OLoggerD Daemons. So it's recorded. Now question is, why is there a CHM in the first place and where I can see it? So I am saying CRSCTL status resource -t -init. This is nothing but your cluster health monitor tool. It comes from 11.2020. It was not there prior to that. So it comes bundled with your clusterware. Purpose is to monitor all resource utilization on the cluster boxes. More details on it because we have separate set of slides for cluster health monitor tool itself. That time it will be more evident. But as of now, I am interested in this one. The OLogger daemon receives information from all the nodes in the cluster and persists in a CHM repository based database. So purpose is all the nodes will send the node specific monitoring data to OLoggerD daemon, and that OLoggerD daemon will accept it and will store it in the Berkeley DB, which is a repository for the CHM. This service runs only on 2 nodes in a cluster. So randomly selected 2 nodes will be picked up for CHM monitoring, and the OLoggerD daemon process will only run on it. And then whatever data is captured by cluster health monitor tool from respective nodes, it will be captured by on a central OLoggerD or 2 node OLoggerD, and it will record this into the CHM repository. That CHM repository is nothing but a Berkeley DB software that comes with your grid infrastructure. Another part of OHASD is system monitoring service, OSysMonD. The OSysMonD, which is a system monitor service, performs the monitoring and operating system metrics collection service that sends the data to the cluster logger service. So understand this. What is the purpose of OLoggerD, the cluster logger? To receive the data and then store it into the CHM repository database, which is a Berkeley DB software. But who collects these metrics? On each node, this operating system monitoring, which is enabled at an interval of 1 second. So every 1 second, system monitoring logs are generated. The CPU utilization, memory utilization, IO utilization, the swap utilization, This data is captured by OSysMon-D, and then where does it send? It does not write on its own into the Berkeley DB or CHM repository. It instead sends to one of the O-logger-D processes. O-logger-D then records it into the Berkeley DB software. This service runs on every node in the cluster. So every node needs to be monitored for the resource utilization from the OS standpoint. It's being done by OSysMon-D. The next one is Grid Plug and Play Daemon, GPNPD. This is the daemon. It is indeed very important. Grid Plug and Play provides access to the Grid Plug and Play profile. A profile is an XML file. So I am taking you where the profile is. So go to the grid home, GPNP, profile, peer, and you would see there is a file called as profile.xml. If I see what's stored in this profile, it's quite unreadable as of now until I use a highlighting. So it's version 8, UTF-8, grid plug and play profile version 1 using some URL, whatnot. Cluster name. Well, before that, cluster universal ID. The version number, profile sequence. The cluster name. The profile location. Then there is something related to the network. It says network ID is this net mask which is associated with the Ethernet adapter ETH0. The purpose is public. Then there is net2 which is of this net mask attached to the Ethernet adapter ETH1. It acts as a cluster interconnect. Then I go further. Then somewhere I see that it stores ASM related discovery string. Remember, there is a init or a parameter in ASM called as ASM underscore disk string, which helps you scan specific disk in a given location, which is very unique specific. In our case, since we have implemented ASM using ASM lib, the ASM disk string defaults to ORCL:*. But in other cases, it would be /dev/hdisk /dev/rhdisk/* depending upon your operating system flavor. So here it says, what is the disk string? What is the lease duration? What is the profile for ASM? Where is the SP file of ASM? Very interesting. What is the digital signature? Which is here. So these are the details stored in the grid plug and play profile named profile.xml. The file is named as profile.xml. It's under grid home GPNP profiles and peer. Understand this. It's very critical component of your cluster web. Provides access to grid plug and play profile and coordinates updates to the profile among the node of the cluster to ensure that all of the nodes have the most recent version of this profile. I have shown you earlier the profile version in our case was version number 6. So this GPNP profile is very important. I have a separate topic coming on it. So we'll discuss then what exactly is the role of GPNPD. Next one is grid inter-process communication, GIPC. I am checking it here. So I can see the process here called as gipcd.bin. It's a support daemon that enables redundant interconnect usage. I told you interconnect is a very critical component of your cluster web. if interconnect IPC or private network, whatever you call it as, if it gets broken, what will happen? My cluster will split into two halves, assuming a 2-node cluster, and it will no longer function as a cluster, because all your GES, which is the global on-queue services or global on-queue cache messages, the block transfer, the cache fusion, all goes via the interconnect. So if the interconnect fails, then the cluster splits. So you certainly do not want that you would be using only one line as a private network. You want to implement some kind of a redundancy on the private interconnect. I told you there are two ways to accomplish this. One, use the operating system concept. In case of Linux, we call it as NIC bonding. In AIX, we call it as Ether channel. In Solaris, we call it as IPMP. People call it as trunking, link aggregation, whatever you call it. So create a bond or a NIC team, and then even if one fails, the traffic will automatically, the OS will automatically activate the other NIC and the traffic will be diverted through it. Purely using the operating system feature of NIC teaming, NIC bonding. In 11G release 2, Oracle also introduced HAIP, the highly available IP, which is a redundancy implementation for private networks, interconnects, purely at an Oracle level. So if one of the NIC fails, automatically the IP, which is the HAIP, associated with that private NIC, will switch from that NIC to elsewhere. So this failure of private NICs purely at an Oracle level, where if a NIC fails, detaching the HAIP from that NIC and attaching it to the redundant private NIC is the job of GIPC, which is a grid inter-process communication. This is the one that actually gives you the highly available IP or redundant interconnect functionality. It's a support daemon that enables redundant interconnect usage. Then there is MDNSD, multicast domain name service, is used by grid plug and play to locate profiles in a cluster, as well as in case of your RAC implemented using GNS, grid naming service, to perform name resolution. The MDNSD process is a background process on Linux and Unix and also on Windows. So I am checking for MDNSD. So it's responsible for locating profiles of grid plug and play. Where are the profiles? And then it's also used in case of GNS based RAC configuration, where public IPs and virtual IPs are not statically assigned. In case of GNS based implementations, those IPs are also obtained via DHCP. So as a pre-configuration, your configuration becomes even more easier. So I don't have to depend largely on my network infrastructure team to provide me a list of static IP addresses for public IP, for virtual IP, and for scan VIP. It will be all obtained via DHCP. Such an implementation of a cluster is called as a GNS based implementation. So the IPs are obtained from DHCP, and a subdomain created within your DNS will be doing the node name resolution or attaching IPs to name to IPs will be the job of your GNS. So when I do not know what is the IP, how to get it from or where to get it from, so multicast DNS then will contact the GNS service which is configured onto the DNS, and the virtual IP is copied on any of the either machines in a 2-node cluster. Oracle Grid Name Service, GNS. GNSD, obviously, will we see this service in our cluster? I am checking here. We don't have it in our cluster because our cluster is not configured using GNS. We have static IPs assigned for public, node VIPs, and scan IPs which we have dumped in case of DNS configuration. So those IPs are IPs published with a fully qualified domain name in case of DNS. So we are not using a GNS configuration. GNS is normally suitable for clusters with nodes more than 8. So typically 8 or more node cluster where I don't want to keep on making a note of public IP, private IP, scan IP of all the machines, or rather public and virtual IPs of all machines plus scan IPs for the entire cluster set. When manual management of those IPs become a pain, especially when the number of nodes are high, then in that case Oracle recommends, why do you do this manual management of IP addresses? They might cause conflicts. You may have been maintaining a huge documentation of it. Instead, why not create a subdomain within your DNS with a glue record? Remember, in our DNS there was a section called as $origin, and within $origin we have published the GNS configuration. That GNS configuration also has one IP. In our case it was 172.168.200.40. That was supposed to be a GNS VIP in the case if you were to implement GNS. In such cases, all the node name resolution happens from GNS. The same thing, I don't know if it is still there, was given as devoragrid.oracleexpert.com was the subdomain delegation, which we have removed. So you will have multiple domain entries in case of search, in case of etcresolve.conf, which is a subdomain delegation within DNS, and this is called as GNS based implementation, typically suitable for clusters where manual management of IP becomes a pain.